All right, I'm just going to go through and continue to do some more examples of the inverse Laplace transform. So suppose I have Laplace transform of G is s plus 1 over the quantity s plus 1 squared plus 9. So again, this looks like something over something squared plus 9, and the something is s plus 1. Right? And I know that the Laplace transform of e to the at times some h is the Laplace transform of h, but I evaluated it s plus 1, or this should be s minus a. So this says my a is minus 1. So this looks like the Laplace transform of e to the minus t times some h is the something over something squared plus 9, where the something is equal to s plus 1. So the Laplace transform of h must be s over s squared plus 9. And from our table, s over s squared plus a squared, that gives us cosine of something t. And so I take the square root of this. So this looks like the Laplace transform of cosine of 3t. So my original function, so this is my h. So Laplace transform of e to the minus t times cosine of 3t is equal to Laplace transform of cosine of 3t evaluated at s minus a minus 1. All right, and the Laplace transform of cosine is this something over something squared plus 3 squared. And the something is going to be s plus 1. So this means then that my g from up here is e to the minus t cosine of 3t. Okay. Now, what did we just do? We had Laplace transform of g is s plus 1 over s plus 1 squared plus 9. The issue here is that what happens if that had been expanded out? So s plus 1 squared is s squared plus 2s plus 1. Don't forget to add the 9. What if I was given s plus 1 over s squared plus 2s plus 10? And the answer now is I have to complete the squares. So the thing to notice I want to add and subtract. So I want to add something and subtract something clever. So this looks like something s plus something squared. What s plus, let's say, b squared is s squared plus 2bs plus b squared. So that means 2s is equal to 2bs, so my b equals 1. And so that's 1 squared. Let me write it out the long way. So here I want to add 1, but if I add 1 here, I have to subtract 1 there. And I have this expression, and this was what I was originally given. And notice in this form, then I can recognize this as Laplace transform of e to the minus t times cosine 3t. So oftentimes, you're given things in this form, and you've got to go through and do the algebra to put it in that form. So the important thing here is for any expression you break into small pieces. You can do lots and lots of algebra. Do it one step at a time. It's extremely important. You need to look for patterns, because the idea is you want to put things into the form of something you already know. And it's going to be really important for you to just be patient, practice, and be persistent. Especially the first time you start doing this, you're going to make a lot of mistakes. You're going to go in the wrong direction, and you really have to get a feel for this and work examples out on your own. Watching me go through and do this is not going to really help you do this. This is a great example of a situation where you have to get in there, do things, make mistakes, and learn from your mistakes. In fact, there's nothing wrong with making a mistake here. It's expected, and it's one of these things you have to do to help you learn. So really be persistent, try things, and if stuff doesn't work, just go back and try something else. That's perfectly normal. Let's do another example. Suppose the Laplace transform of some function g is s over s squared plus 4s plus 18. So there's not an obvious way to factor that, but notice if I can complete the squareds. So I want to add something and subtract something so that this thing looks like s plus b squared. What is s plus b squared? It's going to be s squared plus 2bs plus b squared. So that means my 4s is equal to 2bs, which means that my b is 2, and b squared is 4. So I'm going to add and subtract b squared plus 4. So my original expression was s over s squared plus 4s plus 18. If I add the 4 and then subtract the 4, this looks like s plus 2 squared, and 18 minus 4 is going to be 14. Okay. If I want to use that weird exponential thing, everywhere I see an s, I need to see an s plus 2. And I have an s by itself, but no s plus 2. What did I do here? I added and subtracted the same thing, and that's perfectly fine because if I add something and subtract it, I'm essentially adding 0. And if I had an s plus 2, I could use the exact same trick I used before. So if I had that, I'd be on the right track. But I can't just add something. If I subtract it, though, right? If I add 2 and subtract 2, then this expression is equal to that expression. So let me break this out into 2 pieces to motivate what I get. This looks a lot like the Laplace transform of e to the minus 2t times, what was it? Cosine? Cosine. And this can be the square root of 14t. This is sort of like Laplace transform of e to the minus 2t times sine of square root of 14t. It's not, though, because I would need square root of 14 there in order to make that work. But if I multiply, so up here I added, so I had to subtract. Here I want to multiply because I want something times this. So if I multiply and divide by the same thing, I'm multiplying by 1. And now I've got this extra factor of 2 square root of 14 floating around. Oops, sorry. I'm using this for here, so now I've got the 2 divided by the square root of 14. Let me rewrite this. So what just happened? I added 2 and subtracted 2 to get that term. And I like that because this is now the Laplace transform of e to the minus 2t cosine of square root of 14t. I would like to have square root of 14 over s plus 2 squared plus 14 here. If I had that, that would be the Laplace transform of e to the minus 2t times sine of square root of 14t. Right, but I didn't have that. I had the 2, so I got to be careful. This is a minus. So I bring the 2 out, and I have the square root of 14 here because I need that. So this expression right here is equivalent to this whole expression there. And I need to keep track of these constant terms. So this means then my original function g is going to be e to the minus 2t cosine of square root of 14t minus 2 over square root of 14 e to the minus 2t sine of square root of 14t. So what the heck did I do here? So I started off with this. I recognized that I could not easily factor the thing on the bottom. In fact, if you were to try to do a quadratic equation to factor this, you're going to get 4 squared minus 4 times 18. That's negative, right? So I don't have roots to that polynomial, so I'm not going to factor this easily. If then I decided to use completing the square, I can write it so that I get something over s plus 2 squared plus 14. Now I need to manufacture an s plus 2, because everywhere I see an s, I now wanted to use an s plus 2. And the reason for that is because I know that in the distant future, I'm going to use my properties when I have an exponential times a function. So I add and subtract this. So I get this term, break it up into pieces, and now I've got to do the algebra to ensure that this looks like it's in the form I need, which has an a over s squared plus a squared. So there's a lot of algebra here, and it's going to be really important for you to do one step at a time. I cannot overestimate that. It's really easy to make mistakes. I made a couple of goofs. It's fine. What's important is you recover from it and recognize it, and just be flexible. And again, the first time you sit down to do this, you're not going to know this path, right? I happen to know, as soon as I saw this, I knew in advance that I was going to be using this, and I was going to be playing these games. This is the first time you're seeing this. You've got to just go through and work things out and get a feel for it. Again, there's no replacement for just sitting down and doing this. Okay, so let's do another example. Suppose the Laplace transform of g is 2s plus 1 over s squared plus 9. Right. In this case, everything is factored out nice. So I can think of this as a over s plus b over s squared plus cs plus d over s squared plus 9. Okay. And so the big step here is to recognize I can just go do a straightforward partial fraction expansion. If there was an s term in here, I would just continue to use it and not play with it. And after I figured out a, b, c, and d, then I would try to complete the squares. But for now, I'm just going to try to get these. So what is this? This is partial fractions. I'm not going to go through and do all that simply because it takes a long time, and you're expected to know how to do that. So you should be able to go through and show that this is 2/9 over s plus 1/9 over s squared plus, having trouble with my own handwriting, minus 2/9 s minus 1/9 all over s squared plus 9. So let's see, so this becomes 2/9 times 1 over s plus 1/9 times 1 over s squared. I'm going to break this up into pieces. So this is minus 2/9 times s over s squared plus 9, and that looks like cosine 3t, minus 1/9 over s squared plus 9. This does not look like sine of 3t because I would need a 3 here. So if I want to get a 3 there, I have to multiply by 1/3. So 3 divided by 3 is 1. So let me rewrite this. This is now 2/9 times 1 over s plus 1/9 times 1 over s squared minus 2/9 over s squared plus 9 minus 1 over 27, so 9 times 3 over s squared plus 9. So this is 2/9 times Laplace transform of 1 plus 1/9 times Laplace transform of t minus 2/9 times Laplace transform of cosine of 3t, 3 is coming from the square root of 9, minus 1 over 27 Laplace transform of sine of 3t. Which means then my g of t is 2/9 plus 1/9 t minus 2/9 cosine of 3t minus 1 over 27 sine of 3t. Okay, let's do another example. Suppose I have the Laplace transform of g is 8 over s cubed minus 5s squared minus 12 over s to the 4th minus 16. Okay, I'm just going to try to factor this thing, try to do partial fractions. If I can't do partial fractions, then I'm going to come up with something different. But this is, I immediately see, I'm going to leave the numerator alone, 8s cubed minus 5s squared minus 12. That looks like s squared plus 4 times s squared minus 4. And I can, so again, leave the numerator alone. And notice the numerator degree is 3, the denominator degree is 4, so I don't have to worry about any kind of weird division. S squared minus 4, I can write as s minus 2 times s plus 2. Okay, and I'm not going to be able to deal with that because I can't factor that. So I can now do my partial fraction expansion, make this a over s minus 2 plus b over s plus 2, and then the degree of s squared plus 4 is 2, so I need a polynomial of degree 1 in the top. So now this is going to be my partial fraction expansion. Okay. All right. Again, I'm not going to go through and do all this, but basically set this equal to the thing above, multiply through by the denominator, make some clever choices for s. You should get that a equals 1, b equals 3, c equals 4, and d equals minus 1. Okay. Again, you're expected to know how to do that. So you should be able to write this as 1 over s minus 2 plus 3 over s plus 2 plus 4s minus 1 over s squared plus 4. And now I need to break this up into pieces. So I know how to deal with that. That's just going to be exponential of e to the 2t. I know how to deal with 1 over s plus 2. That's going to be e to the minus 2t. So this is going to be 4s over s squared plus 4. So that looks fine. That looks like cosine of 2t. Now this is minus 1 over s squared plus 4. But if I want to make this be sine, I know I need a 2 there, right, because of the square root of 4. So if I multiply by 2, I have to divide by 2. Right? So this expression, 2 divided by 2 times minus 1, is exactly equal to the minus 1 there. So this becomes the Laplace transform of e to the 2t plus 3 times the Laplace transform of e to the minus 2t plus 4 times the Laplace transform of cosine of 2t minus 1/2 Laplace transform of sine of 2t. Careful. Okay. So that means my g is e to the 2t plus 3e to the minus 2t plus 4 cosine of 2t minus 1/2 sine of 2t. Okay. I'm not going to do any more examples, but at this point you should be asking, why do we care about this? And what does it have to do with ordinary differential equations? And the answer is the same answer to almost anything important or anything interesting, is integration by parts. What is integration by parts? So if you took calculus, you probably saw that formula somewhere, which is a really dumb formula. I hate this formula. What is this integration by parts? Integration by parts is, you notice that the derivative of f times g is f prime times g plus f times g prime. So the thing on the left must be equal to the thing on the right. But the integral of the derivative of something is just the something. And I can break this into two different integrals. Like that. And if I solve for one of those integrals, so let's solve for this one, the integral of f prime g of t dt equals f of t g of t. I'm going to be careful here because in real life it's rare to just deal with indefinite integrals. Let's go back and make everything a definite integral, because that's far more interesting and more important. So this becomes the definite integral of f prime g, and I include my bounds here, and I subtract the integral from a to b of f of t g prime of t. And your Calc 2 instructor probably did some dumb thing and said, let me call f prime dt dv and then g a u, and that's where this uv minus v du comes from. Thinking about integration by parts this way is a far more important and more powerful idea. And notice, there's a way to interpret this, is I have a derivative on f prime, and what I'm doing is I'm taking that derivative off of f and sticking it onto g. And I got to be careful. This should be a dt, right? But it's going to include this crazy bound. So what? What if I had the integral from 0 to infinity of y prime times e to the minus st dt? So from above, this is like my f prime, this is like my g. Well, this is going to be equal to, so I take the derivative off the y, and then take y times my g minus the integral on my bounds. So my f is going to be y of t, and then I'm going to have a derivative with respect to t of e to the minus st dt. So let's clean that up. And by the way, this infinity business is an important technicality. We're assuming all of these things exist and we're taking proper limits. So if I go through and take limits and make sure everything exists, then we're okay. So this becomes y of m e to the minus sm minus y of 0 e to the 0. I'm going to have minus 0 to infinity y of t. The derivative with respect to t of e to the minus st is minus s e to the minus st dt. If s is greater than 0 and this limit goes to 0, again, this is a big if, but if that is true, what do we get? So we leave the left, notice we've not done anything to the left-hand side. This becomes minus y of 0 times e to the 0 is 1. Minus, now I bring out the minus s, that's a plus s. And I can do that because this is an integral in t. So this Laplace transform is equal to this thing on the right-hand side. So let's rewrite that. So we just showed that this is true if certain things are true about the behavior of y of t as t goes to infinity. What do I notice? I notice that this thing on the left is the Laplace transform of y prime. This thing here is the Laplace transform of y, and these both come from the definition. Which means that I can take if I take the Laplace transform of y prime, I can rewrite it in terms of the Laplace transform of y. And so why do we care about that? That was one of the very first differential equations we saw at the beginning of the semester. And we found that there's many ways to do this. We could do integrating factors. We can treat it as separable. We can make a guess. There's a lot of things we could do here. We can also do it with Laplace transforms. I can just take the Laplace transforms of both sides. This thing on the left I can write in terms of this new formula. So I get this, and now notice I have a Laplace transform of y there and right there. If I can get a formula for the Laplace transform of y, I can use this stuff we just did to go backwards to get y. So let me subtract Laplace transform of y from both sides and add y of 0 to both sides. can factor out a Laplace transform of y. And then divide by s minus 1. But Laplace transform of e to the t I already know is 1 over s minus 1. So this is saying the Laplace transform of y of 0. By the way, y of 0 is just a constant. So the Laplace transform of y of 0 times e to the t is going to be y of 0 times 1 over s minus 1. So y of t is y of 0 e to the t. And notice I don't have any constants from integration. There's no solving for initial conditions. If you give me the initial conditions, I immediately work with that. And what we're going to find out is that this thing is an extremely powerful idea. And notice the Laplace transform of y double prime is the Laplace transform of the derivative of y. So I can use this recursively, and I can deal with second, third, fourth, and higher order derivatives.